Okay, we're now into week 5, and we've got one more section in chapter 4, actually 2 more sections in chapter 4, but this is really the last of the applications of derivatives. Section 4.7 will be introducing you to what's called an antiderivative, but in section 4.5 we're going to do applied optimization, and this is really kind of where we've been heading to as far as the application of derivatives. This is the main, most important application. So how do you solve applied optimization problems? Basically, optimization means you want to find the maximum or the minimum value of some function. So we know how to do that in general. We've been working with that quite closely. Now it's about applying that to a specific word type problem. So we read the problem, read it till you understand it, what's given, what's the unknown quantity to be optimized, draw a picture, label any part that may be important to the problem, introduce variables, list every relation in the picture and in the problem as an equation or algebraic expression, and identify the unknown variable. Write an equation for the unknown quantity. If you can express the unknown as a function of a single variable or in 2 equations and 2 unknowns, that is what you really want to be able to do. Sometimes that requires considerable manipulation. I'm hopefully not going to do too much manipulation to you, and all your homework should be similar to the examples. Test the critical points and endpoints in the domain of the unknown, and that's the idea, which is what you basically learned as far as how do we find the minimum or maximum value of a function. Okay, so in our first example here in section 4.5, example 66. So we'll read the problem first. An open top box is to be made by cutting small congruent squares. That means the same from each corner of a 12-inch by 12-inch sheet of tin and bending the sides up. So how large should the squares cut from the corners be to make the box hold as much as possible? So the picture is you draw this square, it's like a tin sheet, and then we're going to cut small squares from each corner. And now it said congruent means they all need to be the same size, and the square has the same sides too, so each side will call its unknown side value x. Okay? And it's a 12-inch by 12-inch sheet of tin, and then we're going to cut those up. You can imagine cutting those out and then folding up the sides, and now we have a box. So what we want to do is we want to maximize the volume of that box. We want it to hold as much as possible, such that we want to cut out these squares just right so we get the maximum volume. So not knowing what size these squares are going to be yet, we call each side x. So what's the volume of that box? The volume of that box would be length times width times height, right? So once you cut out this, the length of the box and the width of the box will be the same. So this whole side was 12. So without the 2x's there, it's going to be 12 minus 2x for this length right here. And this length will also be 12 minus 2x. So the bottom of the box will be 12 minus 2x times 12 minus 2x, and then the height of the box will be x. Once I fold it up, that will be x. So the volume will be 12 minus 2x squared times x. And then the largest x could be is 6, right? Because it only can go up to half. Of course, that wouldn't be a maximized volume because then you would have no box. It would fold in on itself. The smallest x could be a 0. But it could be 0, it could be 6, so it's possible. So we can include those endpoints. And when you include the endpoints, that's what we want to do, because when you include the endpoints, we know that all we have to do is test critical points and endpoints, and we know that the maximum and the minimum will be at a critical point or an endpoint of a closed interval. So that's a pretty simple function. Take its derivative, simplify. You essentially see that you get 12 minus 2x times 12 minus 6x. Set each piece of those equal to 0, you see that x equals 6 or x equals 2. So x equals 2 is the only critical point because 6 is an endpoint. So then we check the endpoints and the critical point. So the volume when x is 0 is 0, the volume when x is 6 is 0. We kind of knew that intuitively from our picture that it would not occur at an endpoint. So the volume when x is 2 is x times 12 minus x squared, so 2 times 12 minus 4 squared. 2 times 64, 128 cubic inches. Thus, the maximum volume is 128 cubic inches when x equals 2, or the cut squares are 4 square inches each.